this self-shading effect for a nice little cylinder here. So then they compared their results simulating Howard Gordon's simple cylinder. And so here's the solid line is Howard Gordon's results and his plus or minus some Monte Carlo noise, and then the little blue squares here are their Monte Carlo code. Xiaoling's Monte Carlo code reproduces Howard Gordon's quite nicely. So they went through several steps to convince you that their code is actually working correctly. It reproduces results from Hydrolite or Howard Gordon's paper, and then they take their code for their real 3D geometry, put it on a supercomputer and burn up a whole lot of computer time and get the self-shading or the shading correction for the TSRB geometry. So keep in mind, the first thing they had to do was convince you that their code puts out the right answers, no minus signs or anything missing. And then you then trust their results after they convinced you that their code is actually working correctly. And what I did on my birthday was I took this really fancy Monte Carlo code I had, and I said, well, I'll throw all this stuff out and simplify it and make something we can use in the lab today. So I threw all this stuff out, then I go back, compare it with Hydrolite. Well, it's not giving the right answer anymore. So I spent my whole birthday trying to figure out what did I throw out that I shouldn't have, that screwed up the calculation somewhere. And then that was my birthday. Then the next day, Sunday, I said, forget it, just go back to this 3D code and I'll just kind of like hardwire some things in that you guys don't need to worry about, but I'll keep the basic code the same. And I did that, and like 2 hours later, it was all checked out and working. So anyway, when I get home, I'll clean the code up, but right now it works, and that's all I care about. So, okay, bottom line is these Monte Carlo techniques are conceptually simple. They're just shooting photons, sending them off in some new direction, recording them at a sensor. They're very general. You can solve any 3D geometry. You can do time-dependent problems, all sorts of fancy things. It's as easy to include polarization in Monte Carlo as polarization can ever be. It's still a mess, but it can be done. And they're instructive in a certain way. You can look at things like what are the distribution of these photons after one scattering, after two scatterings, all of that sort of thing. You can look at, average distances photons travel and so on. So you can't do those sorts of things with Hydrolite. And they're simple to program. That's definitely nice. But, once again, there's Mobley's law of conservation of misery. In Hydrolite, it took years to put the code together, but now you get the answer really fast. Monte Carlo, it takes you years to get the code, it's very quick to get the code working, but then you have to wait years for the code to run, and then you finally get the answer. So there's no magic way to get a 3D problem very fast. You can get 1D problems very fast, but 3D problems, you basically just have to pay your money and wait for the computer program to finish. Okay, like I say, the weaknesses, they can be computationally very inefficient because they're just brute force, ray by ray by ray. And you'll find out, well, you started out with 1 million rays, and you really found out you needed to do 10 to the 8th rays to get the noise small enough to be acceptable. And then instead of like a 5-minute run, you have a 2-week run. And I often have Monte Carlo runs that will go for a couple of weeks just to get whatever I want. There's some kind of problems that they don't work well for. And that's if you have a point or very small source and a very small detector. So let's say I have a little laser here. It's shooting out photons, and I have, let's say, a little radiance detector here that's looking at some little solid angle. And I want to know, what radiance would I measure here? We've got a point source and a point detector, or at least a small source and small one. So there's not any good, or the tricks are not as good to some way get these photons over here, but not waste photons that go off there. There are some ways you can kind of try that, but they get really technical. So that's why I said here, computations of simulation of a small source and a small detector. Likewise, if you want to compute things really deep in the ocean, so here's depth, and here's whatever I'm looking at, let's say radiance. So maybe I want to measure the radiance up here. I'm looking in this direction. Okay, I'm at, 5 meters here. Okay, so I get a lot of photons. If I do backward Monte Carlo, I get a lot of photons from here up to the sky, and life is good. If I move this thing down to, say, 50 meters, and my detector's down here, now a lot of these photons are just going to be lost along the way because they may have so many scatterings that the weight gets to be less than my cutoff, say 10 to the minus 8th, and that photon just never makes it up there. So if you remember, of course, that light fields, whatever they are, they tend to decrease exponentially with depth. And so if I want to go from here to here, I have to increase or send out exponentially more photons to get the same number of photons contributing to my answer. So if you read papers by Howard Gordon, he's always computing ED values. He almost never computes radiances because, and certainly not at depth, because the run times just become so long that it's not worth it. And he didn't particularly need the radiances, so he doesn't ever compute those. Okay, so that's it. So I'm sure if you name a country like China, Uganda, Poland, whatever, you have some mental image of what this place is going to be like. And you go there, you'll find out that it's totally different wherever it is. So, most of us probably have an image of China as being a lot of big cities and polluted skies and a lot of people and so on, but there's a lot of China that looks like this. It's Western China. It's a beautiful country. It's mountains, it's deserts, it's blue skies, very few people. It's just an interesting place to go. So I spent one vacation more or less traveling all through Western China. For those in the back row, we started in Xi'an, we went up through the Gansu corridor, all through Xinjiang, to Turpan, Urumqi, Kashur, etc. Finally ended up just right on the border with Uzbekistan and those countries over there. And so along the way, one day I rented a camel, and we went out and rode around in the desert a while. Very touristy thing, but it was fun. I'd never ridden on a camel before. They don't work at all like horses. Horses do, a left, right thing. Camels move both left at once, both right at once, both left at once. So you go back and forth and back and forth. And it's kind of like being on a sailboat. It goes one way in the wave and it goes the other way. So anyway, definitely when you go to China, don't stop in Beijing or Shanghai. Keep going west. Go to Yunnan province, go to Xinjiang, wherever, and you'll see a whole lot of places that you didn't expect to see. And in fact, the little camel that's hanging on the front of my hat, I bought in Turpan, I think it was, and the camel used to have 4 legs, and then one fell off, and now he's down to 2 legs. So anyway, we'll see how long he goes, but he's in a wheelchair now. So anyway, that's my story for today. So we'll do a lab on all of this stuff this afternoon. And it's 10 after, so come back at 10:30, and we'll do color and stuff, I think it is. You'll get a really heavy dose of caffeine. But the good news, of course, is you get tomorrow off when you would have had to listen to me 2 days in a row, so it's not all bad.